So last time we talked in general about what CFD is about, and it's a subset of scientific computing that is focused on fluid dynamics. And fluid dynamics is governed by a set of equations, and those are actually just derived from basic or the great conservation laws, like Richard Feynman calls them. So the basis of CFD are the conservation laws, and those are conservation of mass, yes, momentum, linear or angular, just any form of conservation of momentum, and conservation of energy. Okay, those are the basic foundational principles that govern pretty much any. This is where you would start as an engineer. What is being conserved, and what quantities you're interested in. So what does conservation mean? Yeah. So if you account for everything, everything should be accounted for. What's coming in should be coming out or should be transformed to heat or something, right? So all changes that happen can be accounted for, okay? And they can be tracked. All right. So we're going to apply conservation of mass, momentum, and energy to a fluid flow. But the problem is, okay, so you need to master these principles. But the problem is that fluids, how do you model a fluid? Right, so when you take Newton's laws, for example, you say, I'm going to apply Newton's second law. Summation of forces is the way you change acceleration is when as you apply a force to a particle, for example. That particle is well defined, right? It's a set of material points that are non-relativistically moving together at the same speed. So that's a well-defined parcel of material, right? So for solids, the model for a solid is somewhat well-defined, okay, if you want to apply the conservation laws. But for fluids, how do you define a fluid? It's just like squishy, and there's like fluid everywhere. It can kind of evaporate, separate, move into droplets, and change. So how do you define, how do you apply the conservation laws to a fluid? Well, it is doable. And but the first thing to recognize is that the conservation laws, what you think of as Newton's laws or the thermodynamic laws, and we had a discussion about this a few months ago, you and I, and with Professor Sutherland. The question is, okay, so when you say m dv dt equals summation of forces, this dv dt, what does it apply for? What does it apply on? Okay, it applies to a set of material points that are collected together and that move together, okay, through time and space. Okay. Now, the great conservation laws are typically defined for a system. That's a well-defined set of material points. So we're going to use the word material point to define an infinitesimal, indivisible portion of a material. Okay. So for a fluid, that is not really easy to define initially because the fluid is just everywhere, right? You put a gas, it's just going to expand. So we have to introduce a new notion for a fluid, and that is the notion of a fluid particle and a fluid element or a fluid system. And so essentially for fluids, if you look at a fluid, this is a cartoon of a fluid flowing around. What I'm going to do, I'm going to pick an arbitrary piece of this fluid, a very small indivisible piece of a fluid that maintains the properties of a fluid. So I'm going to call that a fluid particle or a material point. That's going to be the material point of a fluid. What does that mean? I don't know. It means a bunch of fluid molecules that maintain the properties of a fluid. The point is that's the indivisible, the smallest piece of a fluid you can describe. We're going to call that a fluid particle. And that is going to allow us to apply the great conservation laws to a fluid. But also, at the same time, okay, you can, if you pick a collection of fluid particles and put them together and identify them, imagine you can just tag them. Say, this fluid particle has ID 1, this fluid particle has ID 2, or give them a color, lump them together, and kind of put them in a bag together in an invisible but closed bag that doesn't allow anything to go in or go out. That defines what we call a material element, a fluid element, or a material system, or a fluid system. So it's a collection of particles, of fluid particles, that move around in the flow. Now, as these particles move in the flow, as these fluid elements move in the flow, they're going to deform, either expand or compress, depending on the properties of the flow, but they're going to be the same. So if you look here, this material element at time t0 is here. It's going to look like this, possibly over here. But it is the same material element. For fluid particles, they're going to remain fluid particles. They may deform and change shape, and that is going to tell us something about the forces and the rotational properties of the fluid. So if you do this, if you choose to define model the fluid like this, that allows you to apply the great conservation laws to, you say, I want to apply the conservation law to a fluid particle or a fluid element, fluid system. What is the difference then between the fluid system and the fluid particle? Is that the fluid particle is an infinitesimal version of a fluid system, or the fluid system, the material element, the fluid element, is a finite size version of fluid particles. Both have pros and cons, as we will see as we go along. This form gives rise to the integral formulation of the Navier-Stokes equations, or the equations that govern fluid flow, and this gives rise naturally to the differential form of the governing equations. Of course, because this is infinitesimal, it's very small, it's going to give rise directly to derivatives and rates of change. This is going to be an integral form, right? Because you're interested in kind of the integral properties of what goes on in this blob, okay? Now, if you choose this formulation, and in other words, all the great conservation laws, they are applied to what we call a Lagrangian system. A Lagrangian system essentially tracks particles or material elements as they go in space. Okay, so essentially imagine you are riding on this fluid particle, and as you go through the flow, your properties may change. You may gain speed, or you may slow down. You may experience higher pressures, or you may experience, expansion, right, and lower pressures. So this is the Lagrangian perspective. Okay, that's really great. Now, I just want to reinforce the point that for a fluid particle is essentially an infinitesimal fluid element or system. And for a fluid particle, we're going to define properties just by using the nomenclature delta phi, or whatever that property is. So if this is a little fluid particle, okay, we're going to assign it a property. This could be mass, for example. Delta m is the mass of this fluid particle. So for a system or a collection of these fluid particles, then what is the mass of the system? It's simply the integral over the volume. We're going to use the scripted v to describe the volume of a material element. That's going to be the integral over the entire volume of delta phi. So in this case, for mass of a system, it's going to be the integral of delta m over v. Okay. Now delta m is an infinitesimal property, and that is given by the density times the infinitesimal volume. Now density is an intensive property, so there's no delta rho over here, right? Because it's an intensive property. It's a property of one point or the entire fluid. So there's no delta rho, but there's delta v, because delta v is the volume of this fluid. So you can see now, if you replace this here, you can see how you obtain the well-known formula for the mass of a volume, integral of rho delta v. Rho delta v. Clear? Is this agreeable? So you're essentially adding together all the masses of the small fluid particles. Yes?
When you create a fluid element, so the system, do you have to assume that all of the particles that are in the system have the same properties?
No, they can have different properties in there.
So if you have different, like, let's say one particle has a different.
One particle is oil and one particle is water. Yeah, you can lump them together, but as long as you track them together. It complicates things a little bit. We're not going to assume that right now. It complicates how we're going to apply these laws, but once we get the governing equations, that is going to be irrelevant. So this is just a mathematical formalism to rationalize our derivation of the governing equations, okay? But the point you should make clear is that one day in your research, this is going to hit you. You're going to say, you're going to take the second law of thermodynamics, or the first law, and you're going to say, I'm going to apply it to a fluid system that I have. Make sure you apply it to a fluid element or a fluid particle, because it applies on a Lagrangian system. So make sure that is very clear in your mind. So now for a fluid property, delta phi, the system's corresponding property, or the fluid element, the finite size, is the integral of that infinitesimal property. For example, if the mass is delta m, rho delta v, then the corresponding mass of the fluid element is mass of system. And you'll see I'm going to be using the word cis to describe system, to distinguish system. Okay? Now, obviously, for someone who comes, for example, from a physics background, they may tell you, oh, yeah, let's compute fluids this way. And if you remember last week when we were looking at the excerpt from Harlow's article, when the two top executives were discussing the particle in cell method, one of them was saying, there's no way we're going to have enough computational power to track all of these particles. And that is true, you know. In practice, we can't really simulate an industrial coal boiler by tracking billions of fluid elements. I mean, you have, for these fluid elements to realize a reasonable simulation, you're going to have billions of fluid elements to do a simulation that way. That's just impractical. So we need an alternative formulation. So now we know that we can apply the conservation laws that we know are and are aware of. We can apply them only to fluid elements. But the problem is that in practice, we cannot use fluid elements to do simulations. There are methods that can do this, but you know, they're just academic in nature. But in practice, we know we cannot use the Lagrangian formulation. We would rather use an Eulerian description. What's an Eulerian description? Yes? Yes. So essentially, the Eulerian description says, rather than riding on the particle, okay, and seeing what the particle experiences, you're going to step out of the particle and just look at the space where the fluid elements are moving, and you want to assign a property, let's say velocity, at every point in that volume, in that space. And then the result of that is that any particle with any identity, pardon me, once it hits that point, it's going to assume that velocity or that property that, as an observer, you can see. So in other words, you're going to take, say you have some kind of flow going in over here, right? You're going to stand right here, okay? And you are looking at this region. And for you, this region is just going to have fixed velocity. So the velocity vectors may be like this, you know, something like that, right? And then you will automatically know that as the fluid particles flow through, this one is going to assume this velocity at this point, is going to assume that velocity at that point, is going to assume that velocity at that point. It's just a simple reference frame change, okay? So in physics, this is called the field description of mechanics. So you assume, or you are looking for a field that changes in space and time. In this case, the velocity field that changes in space and can also change in time, okay? And you want to compute that. And that's easier to compute, right? Because then, once you have a snapshot of the system, you know, that's it. You have the solution for the problem. You've immediately identified all the velocities of all or any fluid particle that is going to go through this system. It doesn't matter what particle you're tracking anymore, okay? So cartoonishly, what we're going to do, we want to pick an area of the fluid and draw a rectangle or a volume. This volume could be arbitrary, okay? For simplicity and for the sake of this derivation, pardon me, we're going to pick a rectangle or a cube, okay? So we call this the control volume. You're going to see the nomenclature CV. And we call the boundary of the control volume controlled surface, CS. You should have seen this in your undergraduate fluid mechanics, okay? But this will hopefully reinforce the difference between these two concepts, the Lagrangian and the Eulerian perspective, okay? So now in this control volume, you are looking at this control volume, and imagine this control volume is so small that it only has one velocity, one value for velocity and one value for the pressure, okay? Because you can do 1,000 control volumes or 1,000,000 of those. So if you choose a very small control volume, you can, for all practical purposes, assign just one velocity and one pressure and one density. Then you know that any particle going through that control volume is going to immediately, instantaneously assume that velocity, that pressure, that density, that energy, that temperature, etc. Okay? Now, that description is very practical and very useful for us. But now we have a dilemma. We know the conservation laws apply to material elements, Lagrangian points, but we want to use the Eulerian perspective. So how can we reconcile the two? So how do we write the laws of physics in Eulerian form? Okay? There's something called the Reynolds transport theorem. We're not going to derive it. I'm going to just spit it out for you. But then we're gonna use it interchangeably as we derive the governing equation. The Reynolds transport theorem allows us to make such a transformation. So essentially, the idea of the Reynolds transport theorem, in a nutshell, if you have a control volume with a controlled surface, as material elements flow through, okay, as material elements flow through the control volume. Now remember, material elements are closed systems. Control volumes are open. So there you're allowed to bring in properties and take them out and accumulate things. Essentially, the Reynolds transport theorem tells you, I am going to account for a property phi, I'm going to account for the change in phi inside the control volume plus whatever is coming in and leaving, the net influx, okay, of matter and properties that are going in. So think of everything, of mass, of density, of temperature, of pressure as information. So as information goes in and out of the control volume, the Reynolds transport theorem tells you the relation between the Lagrangian values and the control volume values. That's it, okay? And the way you formulate it, you say for an intensive property, lowercase b, so what's an intensive property? It's a property that doesn't care about the size of the system. So if you take this entire room or this entire building, the air is going to have the same density, more or less, right? So density is an intensive property. But mass is not, because the mass of air in this room is much smaller than the mass of air in this entire building, right? So in other words, intensive properties are properties per unit mass, okay? So for intensive property, lowercase b, of a system, with a corresponding extensive property, capital B, given by mass times B, okay, then we have the following for the Reynolds transport theorem, okay? Let's take a moment and try to understand this. I'm going to write it on the board, okay? Okay. So for a material point or a fluid particle, we said we have a mass delta m and an intensive property b. For a collection of material points, okay, they all have the same b, right? But their mass is the integral, okay? So now for a property b of the system, so the total b in the system, that is going to be the integral over the volume of b delta m, okay? Because really, b is b per unit mass. Lowercase b is capital B per unit mass, okay? So lowercase b is b over m. It's b per unit mass. And really, to be more accurate, b is del b by del m. Okay? So this means that the total, so think of mass again. Okay, the total capital B in the entire system is the integral of the intensive version of B times delta m, right? Because this is per unit mass. And then integral over V of rho B delta V. Okay? delta V. So this gives us the integral quantity or the total value of B, of lowercase b, in the fluid element. Are we clear so far? The relation between B cis and lowercase b. Okay, is this clear? Okay. So now the Reynolds transport theorem tells us that the rate of change of dB system, so as this fluid system moves in the flow, is going to change properties. Okay, although it's closed, but it's going to change properties. It's going to change volume. It's going to change shape. It's going to expand or compress. Okay, so dB cis by dt. So that's the rate of change of the integrated quantity here. That's really equal to d by dt of the integral of rho b delta v. Okay, keep messing up the v. Okay, right? So b cis is this integral. Now we're going to jump into the control volume. And that could be any control volume in space, as long as you know the surface of the control volume, right? Then that tells us that this is equal to the rate of change over the control volume of rho b dv. Now be careful where the integrals are taking place. This is the Lagrangian volume, and this is the Eulerian control volume. Okay, be any control volume, plus the integral over the control surface. That's the boundary, pardon me, of the control volume of rho b u dot n ds. Okay, so let's dissect this. First of all, you're seeing two symbols for the time derivative, and I'm going to discuss this next. But for now, know that this means the local rate of change in time. So if you're at a point, you're measuring something at a point, you just have a ticker that measures, okay, did we increase, did we decrease? You take the derivative, and you can measure the local time rate of change. This is the integral over the control volume. So if this were your control volume, and you have b over here, this is just simply the integral over this volume. It's no different than this integral, right? This is just a different volume. Okay? This is the integral over the well-defined control volume of rho b dv over this control volume. Okay? Now what is this guy? The integral over the control surface of rho b u dot n ds. Okay. So now, because we're dealing with fluids, we're going to assume that everything is moving at the fluid velocity. So that essentially narrows our conversation to control volumes that are fixed and non-deformable. And we can make control volumes deform and change shape, but it's not going to be relevant for the derivation of our governing equations. Okay, so we're going to simplify as much as possible. So we know now that the property B that we're tracking, this could be momentum, for example, momentum per unit mass. So the property B that we are tracking is going to be delivered by the velocity u to the control volume. So you're going to have u rho b over here, and then maybe v rho b over here, right? So it's going to be coming in and leaving, right? What does this integral do? Yeah, the net flux, exactly. So if you apply this to a control volume, to a rectangle like this, it's just going to be the summation of what is coming in and what's leaving, or minus in plus out. Okay? So that is going to be the net flux of B carried by the velocity u. But I want you to think of this physically. Whenever you see a velocity vector, okay, anything multiplying that velocity vector is the quantity being transported by that velocity. Okay? So that's it. It's pretty easy, right? So that translates a law applied to a system or to a Lagrangian element into an Eulerian perspective in integral form. We'll see how we do it for a differential form. how is this useful then? Remember, the conservation laws, they don't tell you, just they don't give you an algebraic value for something. They give you relations between rates of change. So Newton's law, mdv by dt equals summation of forces, right? Or the change in energy in a system is equal q minus w. So you're talking about rates of change. So we're always going to be dealing with rates of change of a system. So there you go. We're gonna take a conservation law. We're gonna apply it in this form, see what it looks like, and then simply change this form to this form to get the Eulerian version. Pretty simple. Any questions? Many of you have already covered this in grad numerical methods. I know you, and you've probably.
Just material time differentiation and explicit differentiation.
The differentiation?
Yeah, from the
material, yeah.
Material and the spatial.
Yeah. So we're going to discuss, this is a material derivative. We're going to discuss this.
From material differentiation to the spatial.
Yes, but this is an integral form, not the differential form. So the differential form is going to look a little bit different.
Just use the delta delta t as time differentiation.
Yeah.
That's what I said.
Yeah. Okay. Oh, yeah. Okay.
Yeah,
Yeah. Different. Yeah. It's the same. Different. Yeah. From different schools of thought. Yeah. Did you wanna talk more about this?
No.
Okay.
Clear with this.
Okay. Excellent. Okay. So are we all on board? Okay. Okay. So what do you do to obtain governing equations on Eulerian form? We do the following. First, we define the extensive and intensive properties. For example, if the extensive property is mass, if you want to derive the equation for conservation of mass, B is m, and lowercase b is 1, right? It's dm by dm is equal to 1. So that gives you the intensive property, lowercase b equal 1. If the extensive property is momentum, mv, so the intensive property is v, okay? And then apply the physical law on a closed Lagrangian system, for example, Newton's law, or in the case of conservation of mass, we'll see what that looks like. Okay, so for example, Newton's second law tells you that the rate of change of momentum for a system, P, I'm going to call momentum P, is the summation of forces. And P is simply, P system is the integral of U delta M, which is rho U delta V. Okay? Now remember, U is B, lowercase b, and then we get rho U delta V. That's our basic integral form. Okay? So now we know we can apply Newton's law on this guy. So we do dB cis by dt is d by dt of the integral rho U delta V for the Lagrangian volume, and that's immediately going to give us the Eulerian form. And if you've already worked with the Navier-Stokes equations or have taken grad fluids, you can immediately identify this as the left-hand side of the gas dynamics equations. Okay? Now, there's one little trick we can do. We're still kind of just doing some elementary analysis here. We haven't started deriving equations yet. Okay? Now, there's one little trick that we can do to convert surface integrals to volume integrals, because we're going to need it eventually when we try to get rid of the integral form. And it turns out that we can use the divergence theorem to convert a surface integral into a volume integral, and that's simply given by this form. So the integral over the volume of the divergence of a vector field is equal to the surface integral of that vector field dotted by the unit normal. Okay? So that allows us to go back and forth between a surface integral and a volume integral. So you just take this guy, put it inside a divergence. Okay? So then what's the meaning of a divergence? Net flux at a point. Net flux at a point. So let me ask you this. If I have a velocity field that looks like this, okay, at any point in space, so this is the velocity vector u, obviously have two components, u and v. At this point, what is div u? Is it positive, negative, 0?
Positive.
Why? So all of these vectors are the same magnitude, and they're all oriented in the same direction. It's 0, because nothing is accumulating at this point. What's coming in is leaving, right? So that is what this integral is telling you, that the flux is really the divergence. Okay? So in other words, yeah, there's nothing going in here. What about this case? So you have flow like this. What is div u in this case? At this point. So is it 0 or not? No. Not 0, because there is something coming into a point, okay? Is it positive or negative? So let's think of the flux. It's negative. Negative, because u dot n, okay? So if you take an infinitesimal surface over here, the flux really is integral u dot n ds, okay? Now this integral is a signed integral. Could be positive, could be negative, depending on this guy. So if the unit normal is like this, right? This is the unit normal, and the velocity is pointing inwards, the opposite direction. So that's going to be a negative. So a negative flux is actually flow coming in. A positive flux is flow coming out. So then, therefore, so in this case, div u is negative, and that's really equal to integral u dot n. Okay. Now, what about this case? Obviously, div u is positive here. Okay. Just as an aside. Okay. So now the next question is, what's in a derivative? So you see two different derivatives over here, d by dt and a partial by partial t. Okay, so what's in a derivative? I'm going to give this classic example about, you're an environmental scientist in hydrology, and you're interested in measuring a certain level of pollutant in a river close to a power plant that is dumping crap into the river, bad things into the river, okay, poison or red ink into the river, okay, and it's coming in at a fixed concentration, and then it hits the flow, and the flow is going to move it downward, okay. So obviously the concentration is very high here, and then it kind of decreases all the way to 0. But we're going to assume that concentration is fixed over time, that gradient. So all the time at this point, you're going to measure the same concentration, okay? But there is a gradient. There's a difference between this concentration and that concentration. This one is higher. This one is lower. Now, if you, as an environmental scientist, come in and just throw a rope and with a probe and just collect data, you're going to measure one fixed concentration over time. So for the Eulerian probe, so maybe we'll use this board. Okay. So now, this is the power plant, fumes, and this is the river. There's flow in here, and these guys are dumping poison here, okay? You come in, you set a probe, and you measure a concentration of the pollutant C, okay? That's concentration, moles per cubic meter, or whatever you chemical engineers use for concentration. Now, over time, what is the concentration profile going to look like? We said it doesn't change in time. It's going to be a constant, right? No, it's going to be a constant because you're, at one point, okay? So it's going to be constant, okay? But what if this is like the Grand Canyon, and you can't drop a rope that's really, really high. You kind of want to measure the concentration in other ways. And one way is for you to ride on a boat, like this person is doing on my slides. So you're going to go on a boat, and then you're going to drop a probe over here, okay? And this boat is going to float at the river speed, okay? And it's going to go and measure concentration of a pollutant, okay? So what is the profile measured by this person over time? C, so this is C Eulerian, and this is C boat or Lagrangian, okay? What is the concentration measured? If we start here, okay, over here, this is T0. We're starting here. So obviously, the concentration is 0, right? Is 0 until we hit this point, correct? Yep, it's going to shoot up. And then what's going to happen? Yeah, linear, nonlinear, it's going to, it's going to do something like this, right? Okay? Okay. So now let me ask you a question. When this person hits the probe, this Eulerian probe, should they not, based on their reading, should they not measure the same concentration? Yes, of course. Yes, of course, of course. So at some point here, that concentration is going to be equal to that other guy. But how do you account for this change in concentrations? So for this observer, they're seeing a time rate of change of the concentration profile. So if they go and observe this, and they're going to come and report the concentration for their department, they're going to report something like this, and they're like, what? This is different than what we saw here. This is because this has a dc by dt that is not 0. Okay? For this guy, dc by dt is 0, correct? So how do you reconcile the two? This is exactly the Lagrangian and Eulerian problem. Okay? So what we're going to do here, we're going to try to derive a relation between dc by dt, what this observer sees as it crosses the river, okay, and what this observer sees. Okay? Okay, so this is kind of what we concluded. Okay, so we're going to assume that our observer started at, so I'm going to kind of expand this a little bit, and this is our river, okay? And we're going to have, this is the highest concentration, this is where the concentration begins, C0, okay? And then this is at a later stage, this is C1. And we know there's a gradient in concentration that's given by dc by dx. Imagine you know this gradient. And you can measure this. You can go and put probes, or imagine we know this concentration gradient, right? Because the concentration is higher over here, it's lower over there, so there's a concentration gradient in this direction, okay? Now, imagine this person on the boat starts measuring right over here. So they're going to measure a concentration C0, okay? And then when they hit this point, they're going to measure a concentration C1, because we know what these concentrations are, okay? Now, from the perspective of the person on the boat, okay, I want to calculate the rate of change of their measurement of the concentration, delta C by delta T, okay? And that is simply C1 minus C0 over the time it took to travel from this point to that point, right? So you hop on the boat, you hit the first point C0, you start your timer, you hit point C1, you stop your timer, that gives you a delta T. You have the two measurements, so you have all quantities. Okay, but we're going to do some math a little bit to manipulate what this is going to be equal to. Now we know dc by dx, so in other words, we also know what C1 is. From dc by dx, we can say that C1 is C0 plus delta x times dc by dx, right? So we know the rate of change of C in space over x. And over a distance delta x, starting with C0, we know C1 is C0 plus delta x times the gradient, okay? So now imagine these are very, very small, infinitesimal, okay? So that's what I'm going to do. I'm going to substitute for C1. I'm going to put C0, okay, plus delta x dc by dx minus C0 over delta t, okay? So we will cancel C0. what do we get? We get a delta x by delta t dc by dx. But what is delta x by delta t? That's the speed of the person of the boat or the river, really. It's the speed at which you are traveling through the river. Okay, so that's going to be equal v dc by dx. Whoa, this is interesting because now we found a relation between what the observer on the boat is seeing as the time rate of change versus what the real gradient in Eulerian or a field, what the field looks like. Okay, so think about this. The faster you move through your river, okay, the faster you are going to go through these points. So this curve is going to change. This is going to be a function of the velocity at which you travel through the river, right? It's like you're also traveling through the rain. You know, the faster you go, the less rain you're going to collect, right? Or there's like an optimum speed there. Okay? So now, I'm going to add one more thing. I'm going to also say that, okay, what if the company dumped the poison at 8 in the morning and just like dumped a whole bunch for 10 minutes and then they stopped? So obviously you're going to have a gradient in space, but also the concentration is going to change over time. Okay? So for the Eulerian observer, they're going to see something like this, right? Because the concentration is going to change over time as well. And that difference over here is a dc by dt, a local rate of change of the concentration. And we're going to choose to call this a partial derivative because the partial derivative is defined from an Eulerian perspective, essentially. But then the observer here is going to pick up both. It's going to pick up the gradient in space, but also the change in time. Because they started here, and then when they got here, there was also a dc by dt to account for. And it turns out that all you have to do is add this guy over here, okay, dc by dt. But still, this is not the same. This dc by dt is not the same as the local rate of change. So we all agree to call this the material derivative. Essentially, a time rate of change of a Lagrangian material point as you are flowing through a field. So think of this as you have a spatial and time, a spatial field that changes in time and space, and you have a particle moving through it. Different particles at different speeds are going to see different things. So the relation between these two is what we call the material derivative. And we agree to call this, to assign this delta c by delta t, we assign it the simple capital D. And in 3 dimensions, the material derivative is simply material derivative of a quantity, not necessarily just concentration, could be pressure, velocity, is d of that quantity by dt, the local rate of change observed by an Eulerian observer, plus u, the velocity at which the material point is moving, or the relative velocity with respect to the river. But for simplicity, we're going to assume the particle is moving at the speed of the river or the flow. U dot the gradient of whatever quantity. Okay? We're going to call this the material derivative. Okay? Okay. Now, why do we have only a time rate of change for a material point? Why don't we have a spatial rate of change for a material point? So for a particle or for an observer, you can define their position as a function of time. You really don't need, position is irrelevant for a particle, right? It doesn't care where it is. It just has a state and how long it's lived, right? So for a particle that's moving in space, it doesn't care. It doesn't have a concept of location, right? Because for the particle, it's just either feeling something, changing, and how old it is. And so essentially, I'm going to show you a more mathematical way of deriving this guy. So for a fluid particle, all that matters is, so for a fluid property, A, it's given by, it's a function of time, and you can say it's a function of position r, but r is a function of time. So really all you need is to define a rate of change for A, you only need a dA by dt. You don't have a dA by dx. And that's why all the laws of physics are defined as time rates of change. Okay? You don't have a spatial rate of change. But then how do you move this to a Eulerian perspective? You just use the chain rule. Okay? Because A is a function of t and position, if you want. So x of t, y of t, and z of t. Just simply nomenclature, math. If you use the chain rule, you can say this is dA by dt plus dA by dx, dx by dt, plus dA by dy, dy by dt, okay, plus dA by dz, dz by dt. Now for a particle, what is dx, dt, and dy, dt, dz, dt? They're velocities, right? So that gives you dA by dt plus u dA dx, right? Plus v dA dy plus w dA dz, which is in vector form dA by dt plus u dot grad A. Makes sense? This is for those who want to use total differentials, okay? You have both. You can think of it intuitively, or you can think of it purely mathematically. But bear in mind, I mean, it's a question. And it's you know, sometimes you don't pay attention to these things as you are going through. You know, when I learned fluid mechanics, like I didn't pay attention to this. Like, why is there only a time derivative for material points? Well, because there's only time for a material point. Space really doesn't matter because you can define space as a function of time. And so that's why you only see a d by dt. Okay, we don't talk about a material spatial derivative. Okay. Now, is there a relation between the Reynolds transport theorem and the material derivative? So the Reynolds transport theorem was a theorem that related the time rate of change of a system, a collection of fluid particles, as it flows through space. Pardon me. It related the rate of change of the properties of that system, pardon me, to what an observer sees from an Eulerian perspective. Okay? Isn't this the same thing? But what's the difference? The other one was defined for a material system. This one is defined for a material point. In other words, the material derivative is really nothing more than the infinitesimal version of the Reynolds transport theorem. Okay? Okay. Clear so far? We understand some of the basics. Now, finally, we can start hitting the great conservation laws. Do you want to take a minute? Did everyone get candy? You didn't get candy. You can have some candy. Yeah, you don't. Want more candy? Okay. I'll take a minute. Okay. Do you guys know if anyone dropped the class? Can I erase here? Who's seen this before? You kind of, yeah. And where do you see it? In fluids? Okay, okay. How does this resonate with what you saw? Is this more intuitive, less intuitive?
I haven't seen it in the kind of intuitive form that you put it.
Yeah.
Resolve.
Just math, okay. Does that help fix the idea in your mind? Yeah, okay.
I learned fluid mechanics from the continuum mechanics.
Okay.
We need to have the spatial derivative,
Okay, as well?
material derivative.
Yeah, for a spatial material derivative, yeah.
Right.
Yeah, with continuum mechanics.
Right.
Yeah.
We talk about like how to convert. I know math, but I don't know the physics.
Okay, okay. Yeah. Yeah, I come from a mechanical engineering background as well.
Oh, okay.
But I didn't do a lot of solid mechanics, just enough. Okay. So now we will get started with the conservation of mass. And what I'm going to do, I'm going to derive Okay, so for fluid models now, we saw that we have a material point, which is an infinitesimal, indivisible fluid particle, a material element or a fluid system that's a finite collection of fluid particles, a control volume that was the size of the entire fluid, and we can also do a finite infinitesimal, an infinitesimal control volume. So we have really 4 ways of deriving the governing equations. And it turns out as long as you know how you translate from the Lagrangian to the Eulerian form, that's going to give you the left-hand side, okay, of the conservation law. Because the conservation laws are given in the form d by dt of something equal a right-hand side. The right-hand sides are going to be the interesting part of what goes into these rates of change. But for the left-hand side, we can just easily go back and forth between the Lagrangian and the Eulerian form, okay? So we will do this, for the conservation of mass, we're going to do it using 3 ways. We're going to do the Reynolds transport theorem, so essentially apply the principle of conservation of mass for a finite size material element or a fluid system. And then we're going to do it for a finite infinitesimal control volume, okay, a very small control volume, a finite control volume, and an infinitesimal fluid element. So all 4 ways of deriving the same equation. Just to kind of spice things up. I know this is not a fluids class, but gives me an opportunity to kind of let some things sink in and give you also the chance to review through the weekend for next lecture as well, okay? So using the Reynolds transport theorem, it's pretty straightforward. The extensive property we're interested in is mass. So capital B is M, okay? The intensive property is M per unit mass, is mass per unit mass, and that's 1, okay? So lowercase b is 1. Now what is the conservation law for mass? For a fluid element, for a fluid particle. We're not talking about relativistic effects. Is that mass is conserved. Remember, these are closed systems. So once you identify a fluid element, a fluid system, their mass is locked, okay? Density can change, but their mass is locked. So the total mass doesn't change over time. So we can very strongly say that the conservation of mass is given by dm system by dt equals 0. Now remember this derivative, d by dt, that's essentially the material derivative, okay? But for the form of the Reynolds transport theorem. Agree with this statement so far? The mass of a fluid system doesn't change in time, regardless whether we have reactions or not, okay? Because it's a closed system. Now we use the Reynolds transport theorem to convert this into an Eulerian form. dm by dt is d by dt of the integral over the Lagrangian volume, rho dv, right? Because lowercase b is 1. If you remember the Reynolds transport theorem, it was rho b dv, right? So lowercase b is 1. So that gives us the left-hand side. But more importantly, that's equal to partial by partial t local rate of change over the control volume of rho dv for the control volume plus the flux of mass through the control volume, rho u dot nds. So again, what does this mean? This means that the fluid is carrying the density rho into the control volume through the control surface, okay? And if this integral is negative, you have flow in. If this integral is positive, you have flow out. And then you can simply convert this into a volume form using the divergence theorem. And you can combine these 2 integrals, and you get this guy for the conservation of mass. Okay? Do you want me to do it for you on the board? Okay. So now, how can you do this in practice? And you should have seen this in fluids. So if you take a pipe flow, for example, let's see if I still remember how to do this. When you do computing all your life, you kind of forget the basics. So let's say you have a pipe of the non-uniform area. But first, intuitively, I want to ask you something. Has any one of you done gardening before? You have a garden, okay? Do you water with a hose? Okay. So what happens? You take your hose, and do you have like a, you put your finger, I guess, and so what do you do to make the water shoot out at a distance? Yeah, you decrease the area, you put your finger on it. And this is exactly what we're going to show right here, okay? So take a hose and say, imagine the area is decreasing, okay? There is uniform flow coming in, that's U1, and there is flow coming out, U2. This is area A1 with diameter D1, and this is area A2 with diameter D2 is equal to D1 over 2. And the question is, find the velocity V2, U2, okay? So you are given U1, let's say 1 meter per second, you're given A1, you're given D1, find the speed U2, okay? So we're gonna apply the conservation of mass in integral form. So that's what the integral form is useful for, really, for, you know, when you're looking at kind of integral quantities of a system. Okay. So first we're going to define our control volume. I know this is not a fluids class, so you learn these things in fluids, but I just kind of wanted to walk you through an example of this to show you that this is practical. This is actually significant, okay? So if we pick this as our fixed control volume and control surface in the dashed red, okay? The conservation of mass tells us that d by dt of the integral of rho dv, so this is the volume v, okay, over the control volume, plus the integral over the control surface of rho u dot n ds equal to 0, okay? Now this control volume is fixed in time, doesn't change in time, and the density is constant because the flow is incompressible. So that's water, you can't really compress it. So we know that this guy is 0. So that leaves us with this guy. Now what are the surfaces where we have a velocity, a non-zero velocity? It's A1 and A2, okay? It's just these surfaces. So this integral is really the summation of rho u dot n times the area, okay? And that's equal. So for this guy, the unit normal is pointing in the negative direction, right? So n is equal to minus 1, 0, 0. Okay, so that tells us this is minus rho u1 times a1. Okay? Is this correct? Yes. Plus, on the outside, on the other side, the unit normal is 1, 0, 0. So the flow is coming out. You're going to have rho, same velocity, u2, a2 equals 0. Densities cancel out. And then you have a simple statement of mass conservation that u1, a1 equal u2, a2. And therefore, u2 is u1, a1 over a2. Okay? Now, a1 is pi d squared over 4. And a2 is, so a1 is pi d1 squared over 4, and a2 is pi d2 squared over 4. But d2 is d1 over 2. Okay, so that gives you pi over 4 times 1 over 4 times d1 squared. Agreed? Okay, so now we have u1 times, what is a1? Pi d1 squared over 4 over, what is a2? Pi over 4 times 1 over 4 d1 squared. Okay, so pi over 4, d1, d1. You get u1 over, you get 4u1, sorry. 4u1. That makes sense, right? You shrunk the area, it's going to shoot out faster. In reality, that's all because the density is constant. If the density were not constant, something else would happen, because that guy will not cancel out. Okay, it becomes a little bit more complicated. Okay, clear? Kind of just grounds this in your mind. Okay, but in CFD, we're not interested in this. I mean, that's a quantity we may look for to validate our results. But what we're really interested in is what happens here. Does the flow kind of move like this, or what happens in here, point-wise? Okay, that's what we're interested in CFD. Okay. Now, conservation of mass using a finite control volume. So over here, I'm not going to invoke any of the great conservation laws, because in this case, it's kind of easy to kind of do the derivation for conservation of mass. So I'm not going to invoke the a material element, etc. I'm going to say, you know, conservation of mass says everything that comes in and accumulates and then leaves must be accounted for, because mass cannot be created nor destroyed. Okay? So the idea is I'm going to pick a control volume of a finite size. Okay? So this is a large control volume, not infinitesimal. It's a large control volume. And the statement for conservation of mass is that the rate of increase of mass in the control volume is equal to the net influx of mass. Okay, so be careful of what I mean by this. Okay, so because that's going to help us say is this in minus out or out minus in. I mean, this can be confusing. But the rate of increase of mass is going to be in minus out, really. Okay? So we're going to do this in integral form. It's very simple. The total mass at any given time in the control volume, you agree that it's the integral of the density times the volume, right? Because the density is mass per unit volume. So you integrate the density over the volume, that's going to give you the mass, right? Okay, so that's the total mass. Now, what is the rate of change of mass? Locally, it's dm by dt. And that's a local derivative because that's an Eulerian perspective, okay? That's partial m by partial t, and that's simply d by dt of this integral, okay? So that gives us this guy, the left-hand side, the rate of change, okay? Now, what about the flux at the boundary, the flux of mass? Obviously, mass is coming in and mass is leaving. Mass is being carried by the velocity, u, and so the flux is really rho times u, okay, being brought in. But this surface could be complicated. I drew a very simple rectangular surface over here, and if you blow this up, right, you're going to have fluid coming in at an angle, not necessarily perpendicular. So that's really why you take the dot product with the unit normal to only account for the component of mass that is entering the volume, and also the component of mass that is leaving the volume. Okay? Mass entering is negative, and mass leaving is positive. Okay? So, but you have to agree that rho u dot n, that is kind of the fundamental unit of mass that is being brought into the volume. Okay? Mass per unit volume. Okay? So then the net mass that is coming into the control volume is just simply the integral of rho u dot n ds. Okay? That's the net flux of mass. We don't care now if it's positive or negative. The net flux of mass into a volume is the integral of rho u dot n ds. If that integral is negative, we have mass coming in. If the integral is positive, we have mass leaving. So in general, the flux of a quantity is u phi dot n ds. Okay, if the flux is negative, then it's coming in. If the integral is negative, it's coming in. It's positive, it's coming out. And then finally, that's it. That gives us the conservation law. The rate, phi is a quantity, any quantity. Density, momentum, yeah. So it has to be, yeah. So we call this phi in mechanical and chemical engineering fluids. Phi refers to anything. Okay. Now sometimes it doesn't make sense. You know, sometimes you have to adjust what phi is. You know, you can just use any quantity, but pretty much that kind of defines the flux of a property phi being transported by u. That's the flux. Okay. And then, you know, what do? You just equate the two. The rate of change of mass in the control volume is equal to the flux. But then let me ask you this. Why do I have a negative sign here? Yeah, but why? So I said, so for mass, if we are putting in more than is leaving, then the rate of change in the control volume should be positive, right? And if we are putting in, that integral is negative, so we multiply it by a negative sign to make it positive, right? Yeah, you can interpret it this way, but you know, for me, the way I think about this is the rate of increase. If we are putting mass in, if all mass is coming in, then this guy needs to be a positive quantity, okay? But what is this guy? If anything is going in, this integral is negative, so I have to multiply it by a negative sign to make it positive. And then if things are leaving, that integral is positive, multiplied by a negative sign makes it negative, which makes the rate of change decrease. Okay? All right. Let's do a couple more. Now we're going to take an infinitesimal control volume, and maybe I'll do this on the board with you. So this is one of the derivations you will see in your undergraduate and also possibly graduate fluid mechanics. So now rather than taking a finite size control volume, and doing an integral, we're going to take the smallest, a very small, indivisible control volume, whatever that means, indivisible. But from an Eulerian perspective, we're going to pick a very, very, very small infinitesimal control volume. Okay? And if I can draw in 3D, let me see. Okay. To show that these are kind of in the back. Okay? Okay. So now this control volume, I'm going to assume it is so small that there's no change in properties inside the control volume, only outside. Okay, so from one control volume to another, there is a change in properties. But I'm going to assume that at the center, actually we need to assume that there is a change, and then we're going to shrink everything in the limit. Okay, but then at the center lives a density and a velocity assigned to this control volume. So U, V, and W. Okay. So now rho U is the quantity of, is the mass flux that is coming in and leaving the control volume. Okay. And given that you have rho and U at the center, you can also compute rho U at the center. Okay. Now how does this rho U change as you move a distance delta x over 2 or delta x over 2 in each direction? You can just simply use Taylor series, right? So what does Taylor series do? What does Taylor series tell you? You can expand, okay, around any point. So given values at a point, you can compute the function at any neighboring point using that point. Okay? Do you remember? Does anyone need to remember the Taylor series? Taylor series, yes. Taylor series. Yeah. So yeah, f of x is equal f of x0 plus x minus x0 f prime at x0 plus 1 over 2, okay, factorial, x minus 0 squared, da, da, da. Okay? So that's the Taylor series. So essentially, this is saying if I know the value of a function at a point x0, the value of its derivative at x0, the value of its second derivative, and all the derivatives at one point, then you can deduce or compute the value of that function at any neighboring points, at any neighboring point x. So if you know everything about a function at x0, you know f of x0, f prime at x0, etc., then you can compute that function in a neighborhood, x, or a distance x minus x0. Okay? So this is what this is telling you. Okay? So here we're going to say we know rho u. We know rho u in the center. So what is rho u at a distance delta x over 2? So in 2D or in 1D, just to simplify things for you, this is what we're looking at. In the middle, I have a rho u. And over here, I have, rho u out. And over here, I have a rho u in. But I don't know what they are. Okay? I don't know what they are. So starting with the knowledge of rho u at this point, this is x equals 0. And this is a distance delta x over 2. And this is at a distance delta x over 2. Then we're going to write rho u in as a function of rho u. Okay? Does this make sense? Yeah. So then rho u in, we're going to expand in Taylor series. It's going to be rho u at x0, or in the center, okay, minus or plus, okay, plus x minus x0. That is going to be minus delta x over 2, okay? Because this is minus delta x over 2 minus 0. Okay? So that's, yep, of, so that's going to give you minus delta x over 2 of what? Of d rho u by dx. Okay? Now, we need to multiply this by an area, okay? Because that's a mass coming in, right?
Is this also the base for the finite difference method?
Yes, yes, but we're going to derive the governing equations first, and then we're going to apply finite difference. Okay. Okay. So that gives us the flux that is coming in. We just need to multiply it by the area, which is delta y by delta z. Okay, so that area over there. In other words, this area, okay, or this area. Is this clear, Aaron? Got it? Okay. So we multiply by delta y, delta z. And we do the same thing at the plus face, or at the out face. Rho u out is going to be equal to rho u in the middle plus delta x over 2 d rho u by dx plus a bunch of other terms times delta y, delta z. Okay, so that gives us these two terms. Because we assumed we know the value in the center, and we're going to say, okay, what does this lead us to? We don't know the value. We don't know how much mass is coming in. We don't know how much mass is coming out. But we don't care, because what we are after is a balance. We want to make sure that the rate of increase is balanced by what's coming in and what's leaving. Okay? So then you do this for all sides. Okay? And then we said that the law of conservation of mass is the rate of change of mass in the control volume. What is that? So what is delta m? So this finite control volume has a infinitesimal mass, delta m, which is equal to rho delta v, which is equal to rho delta x, delta y, delta z. Correct? That's the infinitesimal mass of the small control volume. And then conservation of mass tells us that d delta m by delta t, which is d rho delta v by delta t, or delta v d rho dt, because delta v is constant, right? You agree that this volume is fixed, non-deformable, delta v d rho by dt, is equal to the net influx of mass. So in other words, in minus out. So what is in minus out? Rho u in. So that's going to be equal to rho u in minus rho u out plus rho v in minus rho v out. Okay, so sorry, I did not describe what we're going to use to refer to the velocity field. So the velocity vector u, we're going to refer to it as u v w. U is the velocity in the x direction, v is the velocity in the y direction, w is the velocity in the z direction. So now all you have to do is sum up all the fluxes. You go through the algebra, do it yourself. You know, you get this. And see how delta v is going to cancel out very nicely. And then you get the conservation of mass using yet another way to derive it. Okay? All of them are the same. So if we go back a few slides, so this is d rho dt plus div rho u, okay? If you go back, this is the integral of rho dv, or d rho dt if you bring in the derivative inside. This guy is nothing more than div rho u, integral of div rho u. And same thing for this other form, integral of d rho dt plus div rho u, okay? They're all really the same, okay? And there's just one last form that is a little bit involved, and you know that may show up on one of your homeworks, but that's essentially applying the mass conservation for a fluid particle, for a material point. Okay, so if you are tracking a material point, so we already did it for a material element or a material system, a collection of material points. But what is the law of conservation of mass for a material point? So a material point, very small material point, has a mass of delta m, which is rho delta v. what is the conservation of mass for a material point is d delta m by dt equals 0. Mass doesn't change of a material point. Same for a material system. Okay? So now we expand. We say d rho delta v by dt is equal to 0. But that's equal to delta v d rho by dt plus rho d delta v by. Many textbooks will omit this guy. Many textbooks will omit this guy, but we're not going to omit it because this has a very important meaning. This d delta v by dt, the rate of change of the material volume. Okay, so the volume may expand, may change size. It may be the same, but the shape of the volume may change. Okay, so this delta v changes in time based on what? We're going to show, this will be one of your homework assignments. We're going to show that, so this guy, this d rho dt, we know what it is. But this d delta v by dt is actually related to the dilatation. It's proportional to div u. Okay, it's delta v by div u. And then when you do the substitution, you get the continuity equation, the mass conservation equation. Okay? So next week, we're going to do the linear momentum equations. Okay? They just cancel out. Yeah, they're irrelevant. I mean, that's a good question, but they're so, as you shrink this, well, they don't cancel out. They are the high, so as you, in the limit, as delta x, delta y, delta z approaches 0, the only terms that are not multiplied by delta x, delta y, delta z are these terms. So all the other terms are multiplied by delta x, delta y, delta z, or delta v. So as you shrink the element to 0, all those terms disappear. Okay? Yeah, in the limit they're negligible because the leading terms don't have delta. Remember, delta v canceled out. So the higher order terms are going to have a delta v except for these terms, right? And in the limit as delta v approaches 0, all the other terms disappear. Okay? Okay. Thank you for your good attention. I'll see you next Tuesday.